This lecture we would be studying about binary adder subtractor. This circuit will both add and subtract the given n-digit binary numbers. Now this particular figure shows you the binary adder subtractor for a 4-bit number, for 4-bit numbers. Okay. Now this contains the number of XOR gate depending on the number of binary bits given to you. For example, if a 4-bit binary number is given to you, then it will contain 4 XOR gates and 4 full adders. Okay, the structure of this circuit is just like this. We have M as separate input here. We have all the numbers here as input. Okay, we have A0, A1, A2 and A3, the first 4-bit number. In the same way, we also have B0, B1, B2 and B3 as the second 4-bit number. We also have M here, which can be 0 or 1. We also have full adders here to do the addition operation. Okay, we have the summation out here, S0, S1, S2 and S3, and the final carry, that is C4, and we also have an overflow detection here. Okay, we will learn about this overflow detection method. But the operation of this circuit depends on the value of M. If M is 0, then the operation would be the addition operation. It will add the two 4-bit binary numbers given to you. Okay, A of I and B of I. Okay, and in that particular case, C0 would be 0. Okay, now in case of M is equal to 1, the operation would be a subtraction operation and C0 would be 1. Okay, C0 is here. This is tied to M. Okay, so depending on M, that value also reflects on the C0. First, I will explain you the operation of addition, which is very much simple. M is equal to 0. Let me just draw the XOR gate truth table. There goes 0, double 1, 0. Okay, this one represents you the XOR operation. Okay, for M is equal to 0, you see, for M is equal to 0, we have considered here M as 0 here. Okay, so what you see for all the XOR gates, okay, one value remains 0. And if you look for the table, if one value is constantly 0, then the output is always dependent on the second value. So you can say the output of this XOR gate would be B0, B1, B2 or B3. Okay, whatever the input is, that is going to be output. Whereas the other input to the full adders is going to be A0, A1, A2 and A3. Okay, so full adder is getting all the respective binary bits for addition, and it will give the summation result accordingly with a carry in the case. Okay, if there is any carry. Whereas C0 remains 0 as M is equal to 0. Okay, so this addition operation is pretty straightforward and nothing to understand here. You can look for the book, you'll also get the figure and the explain operation there. Okay, if you want that. But what happens is the case of M is equal to 1. Okay, so if M is equal to 1, C0 always goes to 1. Okay, now this circuit does the 2's complement addition. It does the 2's complement addition, not the 1's complement addition or not the signed binary, sorry, the 2's complement subtraction. Sorry, it's 2's complement subtraction, not the 1's complement subtraction or signed binary subtraction. Okay, now for 2's complement subtraction, what you do is you keep the first number as is, and that's exactly what is happening here. A0 remains as is, A1 remains as is, A2 remains as is, and A3 remains as is. Whereas you take the 2's complement of the next one. Okay, as M is equal to 1, one gate one input of the XOR gate remains 1 forever. So if you see here, if one input of the XOR gate is 1, the other one is the complement of that. If that is 0, the output is the complement of the other input. If that is 0, this is 1. If that is 1, then that is 0. Okay. So that's how you can say we are getting here B complement, B0 complement, B1 complement, B2 complement, and B3 complement. Okay, so we're getting the complement, and also we have a C0 as 1. So if you take the complement and add 1 with it of a binary number, you will get the 2's complement. Okay, so you add the first number and the 2's complement of the second number, and you will get the answer as is. Okay, normal 2's complement subtraction. Okay, so this is what the binary adder subtractor is all about. Now there is an extra circuit here, that is this overflow detection. So to understand that, what you have to do is to first understand what is overflow. You see, it does the 2's complement subtraction only. So first, if you are given, suppose for example, we are given a 4-bit address or 4-bit register, and we have to add design an adder subtractor. Okay, so register is a 4-bit. So if we have 4-bit register, the maximum signed binary number, 2's complement signed binary numbers can be represented with that is like this: from positive 2 to the power n minus 1 to negative 2 to the power n minus 1, and that will equate back to positive 7 to negative 7. That's the range within which we can represent signed 2's complement binary numbers using 4 bits only, and I have also listed here that. Okay, from negative 8 to positive 7. Okay, and we have same address for both negative 0 and positive 0 here. Okay, so total of 16 numbers can be represented here. 16 signed 2's complement binary numbers. Okay, now suppose we consider the case of, let that be, we are going to consider this first case. We're going to add signed binary numbers of positive 4 and positive 3. Now positive 4 is represented as 0 1 0 0, and positive 3 is just like this. If we add it, okay, you will get this number, that is positive 7. Okay, there is no problem with that. If you do the very same thing for the negative numbers, you get the very same thing. Okay, we have an overflow here, but we discard it, and if you consider the rest of the bit, this would be negative 7. Okay, according to the signed binary numbers, that is negative 7 is here, this one 1 0 0 1, that is the 2's complement of positive 7, this one. Okay, you take the 2's complement of that, you will get the negative 7, because as we are following the 2's complement notion. Okay, so there is no problem. The addition you do, the 4-bit registers you have like S0, S1, S2 and S3, and a carry if you have any, but you discard it, as in the case of this, you get the answer with this. There is no issue with that. But what comes as an issue is an overflow. If, suppose for the case of this second case, what we have the answer that cannot be represented with 4-bit registers. Negative 12 is not within the range of this. Okay, it's exactly like here, negative 12. So we cannot represent with 4 bits this signed binary number. Okay, we will see that over this example. We need 5 bits for that. So if you convert the negative 7, you will get this one. Negative 5 would be like this one. If you add it, then you will get this number, which represents you positive 4. That is not the right answer. If you look for the solution, and you have followed the signed binary number notion, you will consider that the first number would be a positive, but that is not the case. Okay, that is not the case. If you go for the, as the answer should be negative 12, and this problem arrives because the answer we are getting, that is not within the range with which we can represent the numbers here. Okay, with 4 bits. The very same thing also happens here. The answer is a negative 4, which is not right because the answer should be positive 12. Okay, we need 5 bit to represent that signed binary number. Okay, this is only the problem with the signed binary numbers. If we will take only simple binary numbers, then we might represent with 5 bits. Okay, signed binary numbers means the leftmost bit is reserved for sign. Okay, so to resolve that, what we have is, we take the carry out of the into the final full adder and carry out of the final full adder, and we XOR that, and we get a V as output signal, and that represents us that there is an overflow, and we don't consider the answer to be right. Okay, if the overflow is 1, then we consider the answer is not right and there is an overflow case. Okay, and whenever that is 0, we say that the answer is right. The signed binary number that we got from this S3, S2, S1 and S0 is proper, and there is no problem with that. So this is your binary adder and subtractor.